To see, let me just turn off one light. Oh, that's right. Is that better? Yeah, slightly better. Maybe off. All right, theater style. Thank you for coming. This is the 42nd meetup of the HPC and GPU Supercomputing meetup. And you are here at the Silicon Valley campus of Carnegie Mellon University. And we're very fortunate to be sponsored by Cirrascale, who are here. There's Chris and Mark.
He's writing the check, so look over there.
All right.
Yay.
Thank you. Well, thank you for the pizza and refreshments. And today we're also very fortunate to have Professor Jimmy Zhu here with us, telling us a little secret about some of the interesting research that he's been working on all this time. And it could have strong implications about how HPC could be done in the future. So with that, let's get into today's program. So for those of you who are joining us for the first time, in the first half an hour or so, we'll just give a quick introduction of the space, the sponsors, as well as some of the things that happened in the past month as a refresher and help keep everyone up to date. And if you have some interesting things that you'd like to share with the rest of the group, please speak up and share with us. We'd love to learn from you. So Carnegie Mellon Silicon Valley has been here for the past 12 years, almost 12 years now. And we've been developing software leaders here in engineering and business and entrepreneurship. Have many programs in the Masters of Software Engineering and Software Management, as well as a PhD program here with about 50 PhD students. It's only a graduate program here in Silicon Valley, whereas in Pittsburgh we have the undergraduates through graduates. The kids, yeah, exactly. And our meetup's mission is a group for the application of the cutting-edge HPC and GPU supercomputing technologies to cutting-edge business problems. And our emphasis is on the useful application of these technologies by practitioners for practitioners. And we have sister groups all around the United States, Silicon Valley being one of the largest, with more than 860 people in the group today. And a little bit about Cirrascale.
And Chris.
Chris, would you like to? Do you have some slides you wanted to share, or at a later time?
He's going to present.
I'll present after the docs.
Okay.
Okay.
Oh, just real quick, we'll do a quick commercial. Thank you, everybody, for having us. We got excited. We didn't know this group existed. We had stumbled over it on the internet, so we jumped at the first chance to sign up and sponsor the event. We do a lot with GPU-based computing. Mark will talk about that later on this afternoon. Established platform. We're on our third generation of a GPU pairing platform. So we'll talk about custom solutions around GPU scale, around GPU pairing. We have a patented vertical cooling rack that's air-cooled 35 kilowatts. That can house up to 96 GPUs. So I think we've got some cool things to talk about. And then you were actually going through some APM slides. So
we'll get to that.
Yeah. So one of our big claims of fame was in conjunction with NVIDIA and APM 2 months ago, we launched the first twin server that was ARM-based XG NVIDIA GPUs. K20s are supported today. So
nice.
we'll show you a little sneak peek of that.
Great.
Thank you. Thank you for having me.
Thank you. All right. So if you weren't with us for the last meetup, here's what you missed. We had a great meetup with some deep neural network training and deep neural network learning experts with us, namely Dave Sullivan and Rajan Naik. And they have a little startup that is doing deep neural network training on GPUs as a service for any clients who would like that kind of service. And then we also had Dr. Brian Catanzaro present to us about the state of research on the deep neural network research on GPU. And he joined us from Baidu, who he recently joined, but previously he was at NVIDIA as one of the research scientists. But today, we have in our program the M-Logic, all spin devices and circuits for future HPC, presented by Professor Jimmy Zhu later. But first, let's talk about what's new If we look around, I'll just do a little bit pitch about CMU, some of the research that have been going on at CMU. Well, in terms of the kind of programming environment that we use, often there is the one domain-specific language that's used in specific domains. But then now in terms of the wide variety of the applications that we need to program towards, there's often the need to combine different languages into designing the same application. In that process, there was a paper recently that came out about safely composable type-specific language by Omar and many of the researchers at CMU. And they won the Distinguished Paper Award at the European Conference on Object-Oriented Programming. The problematic practice that people have put together with, as you can see, with many of the OpenCL and many other languages, where you have one dominant language and you paste in these strings that are for another language, and then the compiler would take those strings and compile it into another, compile it with another backend, and it happens all over the place, like in web programming as well, where people are pasting in chunks of SQL commands in a Python language, etc. So, but why didn't this show up? Anyway, but
again, then it'll probably still.
Yeah, I know.
The danger is you lose the string.
Yes, danger is a.
Yeah, that's right.
That's right.
The string is gone.
The danger is that you lose the string, or you type something that would say, clear your table or delete your table or something, or a SQL table, or do something nasty to your program, and it's hard to detect that at programming time. And what they did was Wyvern. Is that how you would pronounce it? Huh? Wyvern. There you go. It's a language for engineering mobile and web applications, and where the data type is for a first-class citizen, where they would pass data types around, but then have different scripts or programs operate on those data types. And that way, they have a safely composable type-specific language. And it'll be interesting to see how those would carry over to HPC and all the OpenCL type programming paradigms. Anybody here who has looked at those in that combination? All right, that may be some good, interesting research topic for the professors in the room. And then there is the data center going SSD in DIMM. That is an interesting development by SanDisk, where they have this slot that looks like a DRAM chip, but it actually has SSD on it. And apparently, with this kind of interface, they can get sub 5 millisecond write latency at the DIMM level, and it can enable a lot more storage to be placed in a system where it can be accessed much faster than something that could be, not faster, but with lower latency as compared to the PCI Express.
That's microsecond.
Yeah, but
Microseconds, right?
Yeah.
It's not milliseconds. Yeah.
that's
Thank you. Typo.
Actually, there's new technology where they combine DRAM with the SSDs inside the same chip, and the SSDs are just there to provide
Robustness for loss of power? Or?
Well, yeah, in case the power goes down,
Yeah. So they and Supermicro did the test with the 200 gigabytes and 400 gigabytes capacities. That's huge for a lot of the database-oriented applications. And it's also huge for some of the machine learning algorithms as well, when you can do a lot of iterative algorithms where the data set could be kept in memory rather than dumped to disk. Yeah, good. And then there is also something about Charm++. Anyone is familiar with this piece, Charm++? Well, apparently it's some technology from UIUC that is where they're actively meeting these kind of challenges with the power, energy, reliability challenges by leveraging the adaptive runtime systems of the Charm++ programming model. And what they were doing was like looking at this petascale machines with a lot of mean time between failures, And they were looking at, this last part. Yes, they were looking at regulating the power levels, the voltage levels, in order to control the processors so that they're maintained at a specific temperature, so that they don't use too much power and start failing more frequently. And there is actually a similar piece of technology that's developed by one of my friends at MIT, actually, looking at even a deeper level integration with this, looking at how he can model different computations to be easily checked, so that he can actually run things with failure, but detect when failure actually started happening, and only scale back at that point in time. So there's a lot of research in that particular area with HPC today. And also, we actually had another speaker planned for this month, Dongping, and she had to pull away because...
Dibs on her time.
That's right. Because she was actually going to talk to us about stack memory. But she had to go to Hot Chips. But she did send over some slides from Hot Chips from early this morning. And I'd love to share some of those with you in case anyone is familiar with those kind of technologies and would like to share with us what's going on. So there's quite a few of these. So there is the XX ACE chip processor, NEC's brand new vector processor. Anyone has any background on those? Please.
Well, actually, I don't have background on that particular chip. So,
So what's your affiliation with NEC's vector processor?
well, actually, I wasn't. I just have some VLIW chip experience way back, but not related to the NEC chip at all. I'm sorry.
Great, no problem. Yeah. So there's quite a few more that's interesting. So the Spark 64, Fujitsu's next generation processor for HPC.
GK, they're not showing it.
Oh, I'm sorry. Oh, they're not. I've been having more of a fun looking at all these pretty graphics on my laptop. There you go. Anybody know a bit about that?
Oh, yeah.
Oh, yeah?
Can't tell you anything, no.
So they actually licensed from the Spark 64. You can see that the Sun Microsystems Spark 64 processors, and these processors have been actually quite high on the profile of HPC. For example, there were not this generation, but the previous generation was using the K computer. That was for a period of time the top supercomputing in the world, and it's great to see that there are next generation developments going on in that area. And something interesting for those of us who's interested in doing what happened?
Molecular dynamics.
Molecular dynamics. That's
Wonder
right.
how I guessed that.
No.
So any color on that?
I'm not allowed to say.
We have a lot of those experts with things they cannot say. But just the background for, so who knows about D.E. Shaw? I mean, the name D.E. Shaw, people do recognize, right?
They're a hedge fund.
The hedge fund, exactly.
Yeah.
So this is, we had, when I was at Berkeley doing my PhD, Professor Shaw actually came by to visit our parallel computing lab for one day. And we actually had like a face-to-face meeting. It was quite an interesting experience. But, I mean, this is like a $50 million a year hobby of his. Right. Since he, it's very noble of him to devote his time and resources to molecular dynamic research.
Nah.
But that's a pretty expensive hobby.
When he went to Wall Street, they told him, "You'll never get tenure now." He had the last laugh.
That's right. Yeah, that's always a good story to tell. Okay, next one. AMD. So also AMD's Cavalry chip Anyone has some insight on the AMD cavalry chip?
Yeah, they're a partner of ours. We're doing a launch with them soon of something similar that we're going to show you tonight. It's an ARM64 chip with integrated GPU that's OpenCL compatible. So if you want to do really neat, low power, extremely low power GPU OpenCL kind of work, you can do a non-Intel variant and a non-x86 variant, and then all of the, Red Hat just announced that they're going to be supporting ARM64 based instructions, so you can get, that means Fedora, free will be available for you as well, and they're really going to give NVIDIA a run for the GPU acceleration in math, so. And there's something else coming up this next week, which you're going to find really exciting.
Yeah. Is this the same chip they were sampling in February?
Yeah, but it's basically ready for production. I expect to see little daughter boards, or hardware test systems that you can go out and play with. And the idea is, how would you like to have 192 of those in a 3U or 4U distributed system, and then multiply that by 10, and that's how many of those you could have in a rack and be under 20,000 watts. Vroom, vroom.
Yes. Denver. Now we have Tegra K1 with dual Denver CPUs. Since you read the white
Sure.
paper?
Okay. Yeah. So I'm not at Hot Chips, and also I'm not an architecture expert or whatever. But this was announced like 4 hours ago or so, and there is a new white paper that's linked indirectly through the NVIDIA blogs and so on. So I did go through that to get the big summary. So K1 is NVIDIA's new mobile chip, effectively, with an ARM as well as a GPU, Kepler-based GPU on it, and that was announced in January and has been shipping now for like 3 or 4 months. You can buy tablets with it. You can also buy development systems with it and so on. The interesting part, though, what's that? Yeah.
It's really fast. I played with the tablet at GTC in March, and it's like, it'll be my next tablet.
Well, maybe it won't. Maybe you want a Denver
Well, yeah,
version instead.
Get the better.
So those have been out, and the NVIDIA Shield 2 tablet is using them, and other programs as well. But the interesting part that was not shipped yet, in fact, it was always kind of a little bit murky, was the version using 64-bit ARM chips, which are the Denver chip, which is NVIDIA's own in-house CPU, and they're finally unveiling what it actually does. They've talked about it before. They even said they'll have a K1 version in January. They showed one off in Jensen's hand, in fact. But this is actually the unveiling of a lot of what it is. So here's all talk about the CPU on this K1 variant. And it's, first of all, of course, it's 64 bits. It's using the V8 ARM instruction set. It is not, and this is an interesting point, it is not actually a licensed core from ARM. It is a licensed API from ARM. It's using the V8 instruction set. It's completely compatible, follows all the rules, but it's actually a full custom core designed by NVIDIA, so it's rather unlike almost anything else that's out there. Previously, they were using, of course, 32-bit, A15 cores. The interesting details of this is a little bit like Apple's own 64-bit version. It's actually a wider superscalar CPU. It's doing 7 operations in parallel. It's in order, it's not out of order, which is usually kind of bad news for a CPU, because in-order CPUs can't do instruction reordering or so on, and 7 wide would just be kind of wasted. But there's a reason that it's 7 wide, and that is they're doing something rather not unique. It has been done in the past, but it's kind of resurged a bit, and that is they have a really complex and unique code optimization engine, and they call it dynamic code optimization. And this is going beyond pretty much what other CPUs are doing. If you're familiar with the x86 instruction set, the x86 is not executed normally by the CPU. It gets decoded into micro ops, and it has its own internal representation on an x86 chip. And Denver does something similar to that. When it's actually getting the ARM instructions, it's not actually running them directly. It's actually translating into its own internal format, its own internal opcodes, using a dynamic engine to do this. But unlike even x86, this engine is really, really complex. And exactly how complex it is hard to say. But Normally, when this is be decoded in hardware, there'd be some optimizations in hardware, but NVIDIA's is actually doing almost effectively a recompilation of this instruction stream. And when I say recompilation, it's effectively like this. They're using an extremely large amount of compute and cache even on the chip just to hold the decoded information. If you take an x86 chip, it will take x86 code and decode up to 190 instructions and reorder those instructions back and forth to try and optimize its throughput. Well, Denver is actually doing this, but doing over 1,000 instructions. It's significantly bigger than x86. And it also has on board a gigantic L1 instruction cache of 128K, which is usually just like 4 times as big. And it uses 128 megabytes of system memory to help cache this. So effectively, the code that this CPU is running has actually been processed and optimized. Loops are unrolled, registers are renamed, and dead code eliminated, all kinds of real low-level optimizations, and including runtime optimization. So it's actually taking running code and benchmarking it and seeing branch predictions and so on to optimize this code and save it all out. And this is why it can get away with in-order operations, because that's such a wide scope. It can actually take and find that much work to do every single clock, and therefore it can actually be really efficient and low power for what it's going. Also, this implies that they can put the clock rate up fairly high, because the actual CPU core itself can be fairly simple, since the instructions have been pre-processed to be easier to implement. So this is actually clocked at 2.5 gigahertz, which is significantly higher than their 32-bit version, which is supposedly a simpler CPU. This is actually a more complex one, yet is clocked much higher and is probably lower power. The downside is it takes more room, especially for the caches, which is why the K1 is a dual CPU as opposed to a quad CPU, but the performance increase is well worth it. Where we'll see this, of course, is in tablets and phones and so on, but we will, I'm sure, of course, not officially announced, we'll also be seeing it in servers. We'll probably be seeing it on GPUs. And I'm sure we'll have racks and racks of them.
God, I hope so.
Yeah, exactly. I think so. It's going to happen. And this looks like beyond a nice CPU. This actually looks like a formidable one. They also show benchmarks comparing it less to ARM chips and more actually to Intel's x86 low-power chips, and comparing very well. Those were NVIDIA described benchmarks, but at least they're comparing them to that, not to other ARM chips. So very impressive. This is all from their white paper. It is just presented by NVIDIA, so of course there is a little bias about how wonderful it is, but I think it looks good myself. So that's what Denver is. We'll see that in HPC coming up, I'm sure. I don't actually know the details about it, because I just kind of skimmed the paper myself. I'm just going to give you the summary.
That's a pretty good
summary.
Thank you.
I want to make one comment on that too. I don't know if people remember or recall who Transmeta was.
I was just thinking of Lynn's first job out of college was Transmeta.
Bill Rojas on the title slide there was the architect of Transmeta. They have a license of the Transmeta technology. Now, I don't work at NVIDIA, so I don't know all the changes and additional stuff that's over it, but that's the baseline for what you're talking about.
Yeah, that's why at the beginning I said that has been done in the past. That's what I was actually implying to. Yeah. Didn't work out for them, but.
Great. So also another presentation on low-cost 3D chip stacking was through-chip wireless connection. Anyone have some color on that? I have no. Oh, there.
I make a very big comment on it. Dave Ditzel and Stephen Lee are also ex-Transmeta employees.
What?
Ex-Transmeta
Ex-Transmeta employees.
Who recently were let go from Intel at the end of last year, beginning of January.
Well,
so I don't know,
now we know where they are.
Here, but maybe.
Yeah. It's interesting, like all these presentations, there's some connection here in the room.
I have heard that people are trying to do wireless from chip design because you don't need a really powerful signal, and the chips are right next to each other. Why not go across instead of under a bus? So maybe that's what they're trying to experiment with. I guess you have to be really well shielded.
CMOS biochips for point-of-care molecular diagnostics. Someone local from Sunnyvale. Any color about that? I have no idea, but it's there. So if you are interested, I'm happy to share the slides. All right, a few more. AMD. Opteron. Here we go. Opteron chip, codenamed Seattle. Any colors on that from anyone? All right. Go to the next one. I think the next one is the one that we were talking about. Oh, actually, one more before that. ARM next generation.
Stacks, Jim?
Is this? Ugh, not yet. This is next generation IP support. High-end. I have to shrink it smaller so that it knows that it's on a smaller screen, and then maximize it. Otherwise, it will maximize it to the other screen. Mike, Paul. Any color on this before we go to the final one? All right, we'll go to the final one. XGen. Would you like to start with some background in the XGen? For the XGen?
The Applied Micro has developed a 64-bit ARM64 chip, and a little different. It's a system on a chip, so you get everything. You get a fabric that's interconnected to memory, to a NIC. The base one comes out with 2 10 gig Ethernet ports, a couple of regular Ethernet ports, serial port, and the prototype board that you can buy from Chris over there in the corner comes from Applied Micro on a little mini ITX, and I'll show you pictures here in a little bit. But what they're really trying to push is for 40 watts, you get a system on a chip that will be approximately 80% of the memory bandwidth performance of a E5 Intel processor, with the power consumption and performance of an E3 1200 series system. And it's going to be supported. Red Hat had an announcement saying that they're going to support it under RHEL soon. And we're happy to, we were just here in town, one of the labs is buying a bunch of these to play with and put GPUs in and flash memory in and InfiniBand and create clusters with this as the core CPU running the cluster, and we hope that more people take a look at it, and you can get the slides and see all the different speeds and feeds, if you will, from that, and I'll show you actual hardware in production in a little bit.
Great. So any other color people want to add to this or other topics before we move on?
May I announce the meetup?
Yes, please.
Okay, so in Data Science Journal Club, we will have next week a session on natural language processing. That will be next Thursday, Thursday at 7.
Thursday.
2 papers, yeah, on natural language processing. I think both are from Google.
Very nice.
Just check it out at meetup.com, Silicon Valley Data Science Journal.
I want to do the same, please. I'm one of the organizers of San Francisco High Performance Computing Meetup. So,
welcome.
I'm a competitor.
No, collaborate.
Next week we're going to have the very first kickoff meeting, and we will have people from Lawrence Berkeley Lab, from the creators of Sanguine Engine, and the pioneers of high performance computing in the cloud, speaking at the meetup. So it's next Wednesday. We specifically wanted to avoid any clashes. August 20th, next Wednesday, 7 o'clock at Rackspace office.
Great. So if you want, please post to this meetup's, what do you call it, the posts or the conversations, so that if people are interested, you know, those are great meetups to be going to. So there is some also some news on the Cray on the Trinity supercomputer was now produced with Haswell CPUs and the future generation of Nice Landing. or the Larrabee Follow-ons GPUs from Intel. And also in computation biology, now in the for the NAMD and VMD, how do you pronounce that, Dan?
NAMD and VMD.
VMD, yeah. They're programs that allow you to simulate a lot of very large biomolecular simulations, and what people now call a computational microscope. And it's serving a lot of registered users in many fields nowadays. And that's also something that was in the news. And yeah. So at this point of the meetup, for people who are joining us for the first time, there are lots of resources online and books that you can reference with OpenCL and as well as CUDA, and also some programming patterns for parallel programming. Yeah, so at this point we can all take an opportunity to share a little bit about ourselves. I've been working in multi-core, many-core parallel computing technologies for the past 10 years. Adjunct professor here at Carnegie Mellon Silicon Valley, also doing some little bit of consulting before. Now actually, I need to update this. I'm head of data science at a startup called Simply Hired in Sunnyvale. And my personal goal for the meetup is to meet great people and stay up to date.